In this question, we are required to determine the operating voltage of diode circuit. The equation involved in nonlinear because it contains an exponential term. Due to this characteristic, obtain the exact analytical solution is difficult. Therefore, numerical methods are applied to estimate the voltage accurately. We use two methods, Newton-Raphson method and also bisection method. In Newton-Raphson method, uses derivative as very fast convergence require and good initial gas. For bisection method, does not require derivative, very stable and reliable, converges more slowly. The purpose of this study is to compare this method and determine which is more suitable for real-time embedded circuit monitoring system. So we go to the next slide, was talking about the objective. For first, our objective was to determine the diode operating voltage by solving the nonlinear equation using Newton-Raphson and bisection method. Second one is to apply numerical technique in solving engineering problem involving nonlinear circuit. Objective 3, to compare the convergence speed and number of iterations required both methods. And the last one, to evaluate the computation efficiency and suitability of both methods for real-time embedded monitoring system. For the Newton-Raphson method, we first define the nonlinear equation as Fv equals to 0. The derivative of the function f prime v is also determined. The interactive formula used is Vn plus 1 equals to Vn minus Fvn over V prime Vn. The calculation start with the initial gas. For every interaction, a new voltage value is calculated until the error becomes very small and solution converges. The advantage of this method is that it reaches the solution very quickly, usually within a few iterations. For the bisection method, we begin by selecting two values, lower bound A, upper bound B. The function value at this point must have opposite sign. This indicates that a root exists between the interval. The midpoint is calculated as C equals to A plus B over 2. The interval is repeatedly divided into smaller sections until the desired accuracy is achieved. Although the method is slower, its guarantee converges if the initial interval is chosen correctly. Next was MATLAB coding Newton-Raphson method. To simplify calculation and improve accuracy, MATLAB is used. The program defines the nonlinear function, compute its derivative, apply the Newton interaction formula, stop when the error reaches the specific tolerance. Using MATLAB reduce manual calculation error and allow faster compilation. So the next MATLAB is referred to bisection method. Similar with MATLAB in user implement that bisection method. The code define the interval, check the sign of the function, calculate the midpoint, repeat and process until converges. The program automatically record the number of iterations and final voltage value. Now we compare both methods. At Newton-Raphson method, advantage is faster convergence, require fewer iterations, more computationally efficient. Disadvantage for Newton-Raphson, require derivative calculation. For bisection method, advantage is a very reliable and guaranteed convergence. Disadvantage for bisection method require more interaction and slower compared to Newton-Raphson. Therefore, Newton-Raphson is generally preferred when a good initial estimate is available. This numerical method have a many engineering application. Example include the electronic engineering. So we can use this method for diode circuit analysis, transmitter modeling, and semiconductor design. Another and that control system. Control system will be used to solving non-linear control equation. And other than that, embedded system and electrical power system.
Assalamualaikum, my name is Julian and my number matrix is S71033. Today I will present a solution for question 3.4. The objective of this question is to estimate the digital count at 1.25 volts using the third order Newton divided difference method and the third order Lagrange method. The result from both methods will be compared and verified using MATLAB. Now, I will explain the calculation process using the third order Newton divided difference method. First, I selected 4 data points that are closest to the target voltage of 1.25 volts, which are 0.5, 1.0, 1.5, and 2.0 volts. Next, I construct the divided difference table by calculating the first, second, and third divided difference. This value were then used to determine the coefficient of the Newton interpolation polynomial. After obtaining the interpolation equation, I substitute the target voltage of 1.25 volts into the polynomial. The calculation produced an estimated digital count of 256.8125 counts. Therefore, using the Newton divided difference method, the digital count corresponding to 1.25 volt is approximately 256.81 counts or 257 counts when rounded to the nearest whole number. Next, I will explain the third order Lagrange method. Similar to the Newton method, the same 4 data points were used to estimate the digital count at 1.25 volts. In this method, 4 Lagrange basis polynomials, namely L0, L1, L2, and L3 were calculated. These basis polynomials were then multiplied by their corresponding digital count values and summed together to form the interpolation polynomial. After substituting the target voltage of 1.25 volts into the equation, the estimated digital count obtained was 256.8125 counts. Both methods produce the same result, which is 256.8125 counts. Therefore, both interpolation methods are accurate and estimating the digital count at 1.25 volts. Slides show the MATLAB code used to verify the manual calculation. The code first defines the voltage and digital count data covered in the question. Then, it applies both the Newton divided difference method and the Lagrange method to estimate the digital count at 1.25 volts. Finally, MATLAB displays the interpolated result and generates a graph to visualize the calibration curve. This allows us to verify that MATLAB results are consistent with calculation. These slides show the MATLAB result in graphical form. At the target voltage of 1.25 volt, the estimated digital count is 256.8125 counts. These results match the values obtained from both the Newton divided difference method and the Lagrange method, confirming the accuracy of the calculation. This slide shows an application of interpolation in a wearable ECG monitoring device. The ECG sensor produces analog signal from the human heart, which are converted into digital data by the ADC. Therefore, accurate ADC calibration is important to ensure reliable measurement. Interpolation method can be used to estimate digital count at untested voltage value, improving the accuracy of the device. In conclusion, both the third-order Newton divided difference method and the third-order Lagrange method were successfully used to estimate the digital count at 1.25 volts. Both methods produce the same result, which is 256.8125 counts, demonstrating their accuracy and reliability. The result was also verified using MATLAB, confirming the correctness of the interpolation process. Thank you for your attention.
Hello, Assalamualaikum and good day everyone. My name is Hafizuddin bin Madin. My matrix number is S66055 and today I would like to present about question chapter 4.2, which involve a solving system of linear equations for a power distribution monitoring system. The objective is to determine the unknown branch currents, that is S1, S2 and S3, using two numerical methods, which is LU decomposition and the Jacobi method. Also compare the solution to know about the converging towards the exact solution. The MATLAB program was also developed to verify the manual calculation using LU decomposition. The system of equation is converted into matrix form, that is A times X equals B. The coefficient matrix A and vector B are decomposed into two matrices, namely the lower triangular matrix L and upper triangular matrix U. As you can see in the slide, using the LU decomposition procedure, the first row of matrix U is obtained directly from matrix A. Next, the element of matrix L are calculated using the elimination ratios. And the final result, as you can see, A1 equals to 0.724, A2 equals to 0.665, and A3 0.430. Next, I will explain about the Jacobi method. Each equation is rearranged so that one variable is expressed in terms of the others. The initial guess used for S1, S2 and S3 equals to 0. The calculation will perform for 3 iterations. As you can see the result for first and second and third iteration in the slide. And then the errors also decrease with each iteration, indicating that the solution is moving closer to the exact value. Next, I will explain about MATLAB implementation. As you can see in the slide, there is the same system of equations were entered into MATLAB. For LU decomposition, the built-in LU function was used to generate matrix L and U, and then forward and backward substitution were performed to obtain the solution vector, and you can get the final result. For Jacobi method, a loop structure was used to perform the iterative calculation automatically for 3 iterations. The MATLAB results match the manual calculation, confirming that the calculation were performed correctly. This shows that the Jacobi method is converging toward the exact solution obtained by LU decomposition. Since the coefficient matrix is diagonally dominant, convergence is expected and the approximation improves as the number of iterations increases. In conclusion, the both manual calculations and MATLAB coding produce consistent results. LU decomposition provided the exact solution directly, while the Jacobi method produced an approximate solution that became increasingly accurate with each iteration.
Assalamualaikum. My name is Yushal Sharfa. Today I want to present about chapter 6, which is a preliminary calculation. Before applying the numerical methods, we first carry out the preliminary calculation. As you can see in this slide, the manual and MATLAB solution. In this calculation, we can see that the answer both of calculations similar, which is N1 6.2434 and 2 5.8259 and 4 5.6971. Next is the trapezoidal rule. This method estimate the area under the curve by dividing the interval into several trapezoid. We solve the integral using three different numbers of segment, which is N1, N2 and N4. The result we 6.2434, 5.8259 and 5.6971. After that, we use Rhombus integration. Rhombus integration improve the trapezoidal rule by applying Richardson extrapolation. Instead of calculation the integrator again, is combine the previous trapezoidal result to reduce numerical error and improve accuracy. The final Rhombus result is 5.650, which is very close to the true value. Finally, we compare both methods using the percentage true error. For the trapezoidal rule, an error decreases as the number of segments increase. This shows that more segments improve accuracy. Rhombus integration gave the lowest error, which is 0.0176. This is proof that Rhombus converges faster and produce a result closer to the true value. Therefore, although the trapezoidal rule is simple, Rhombus integration provides better accuracy and reliability. In conclusion, both methods work well, but Rhombus integration gives the most accurate result.